Hi, my name is Jonathan, and welcome to Implementing Internet Breakouts and Network NAT Translation. So, in many enterprise networks, Internet access is achieved by either going through a central site or accessing the Internet directly from the branch offices. In the SD-WAN solution, we allow you to dynamically select which traffic to route locally to the Internet and which traffic to forward to a central site. Either way, we're going to be configuring network address translation for that traffic. So on the completion of this topic, you should be able to implement a policy for DIA that's dedicated Internet access, if you haven't seen that acronym before. And we're going to describe how to set up Internet access regionally, depending on your site layout. So the selection of which traffic can exit directly to the Internet and which traffic goes through a central site is done by a per VPN basis. A default route exists for each VPN, and it can be injected into that VPN for such Internet access. And you can configure NAT as required, such as for blocking inbound unsolicited traffic. Okay? So, in the first example, the local guest NAT in VPN2 should get direct Internet access with a NAT functionality. Okay? So these guest sites should go straight to the Internet. To achieve this, NAT is configured on the transport side and traffic is sent through this NAT. So we'll actually set up NAT specifically on these local Internet connections. Because NAT is changing actual packet headers, IP and port, this is a data policy. All data policies are implemented as central data policies and are driven through the vSmarts because they affect several sites in the same way. Okay? So, here's an example. The NAT function is configured on the transport side on VPN 0, and surprisingly, it's configured with the keyword that tells us to use this circuit for Internet access. Then we create lists for the VPNs and the site lists. So we're saying that our guest Wi-Fi is VPN 2, all right? And then we're going to deploy this to sites 10 through 15. And the site numbers are not on this guy, but we're talking about VPN 2. Right? Then we supply the data policy. We're saying guest Wi-Fi. We're matching destination ports of 80 and 443. Those are TCP for HTTP and HTTPS. We're action accept. We're allowing that traffic. And we're saying use VPN 0. This guy up here. And default action is also accept for everything else. And then we apply the policy. We can also do this using a prefix. So for troubleshooting purposes and operational flexibility, you're advised to use a static default route to the Internet. The default route to the Internet is known as the NAT route, which you can distribute to other sites for more flexibility. In the transport VPN, VPN 0, we configure the NAT function under the corresponding interface first as follows. Boop. All right. In the service VPN, we define a static default route, but pointing to VPN 0 as follows. Because VPN 0 has the NAT configuration, all traffic following this route is NATed. The NAT route is not redistributed into the OMP, therefore other sites do not learn this route. If a redistribution is required, you must either do the redistribution explicitly through BGP or OSPF. And those configurations are as follows. Okay? And there we are redistributing in BGP and in OSPF. When viewing the VPN routing table, the show IP route VPN, let's say 2 in this instance, for troubleshooting purposes, the static NAT route is visible. Okay? So here's the static NAT route. Okay? Notice the F and S here. That means it is a selected route, which means it's the route you're going to use. Notice these other 00 routes are not selected. Okay? Normally, we'd like to see those. If you actually look at this on the SSH session with a fixed length font, these actually line up so that it'll actually show up under the status here as opposed to over there. But that hyphen there means these are not selected routes. They are routes that are in the environment, but you've selected this one, and this is the one that's active route in the routing table. Also note here the VPN of origin. In this slide, the protocol shows that this is a static NAT route. Also, you can see the next hop interface as well as the next hop is VPN 0. So here's our origin, and here's our next hop VPN. And our interface, our outgoing interface is gig 01. Here you can clearly see that the next hop is in VPN 0 as we configured previously. The other 00 routes, sorry, I'm using that as a phrase. 00 is a 00 route is this guy. That's 0.0.0.0/0. Basically, it's in any route. So the other routes seem confusing at first because they go to two head-end routers, each with two distinct transport networks, colors, right? One's pointing at MPLS, one's pointing at business internet. However, in the last column, you can view the status that indicates that neither of those routes are selected or installed in the forwarding information base, that FS that we discussed before. Okay, the NAT route is selected and is in the forwarding information base. So if you do a trace route, you'll actually see us match that top one. Okay. All static routes, including that static NAT route, have the problem of sending traffic to a black hole if that transport behind it isn't working. So if I have a route to an interface that's down, the route, because it's static, it'll still show up in the routing table. Here what we can do is we can do a tracking of an IP address. And basically this is the same thing as an IP to probe. So for example, so I'm doing in system, I'm saying a tracker for dedicated internet access. And my endpoint is this 203.0.113.1. If you're wondering, that's some experimental range for documentation purposes. Mostly I saw this slide and I checked to see who that was, and it turned out it's just an unusable IP address. Okay? And then we're specifying the tracker here to use it under VPN 0. Basically what we do is we send an HTTP probe. Is sent to that endpoint IP with an interval of 10 seconds. And the sequence is sent one time. If there's no response, the interface tracker static is displayed as down. This right here. And the route is declared invalid. This lets us fall back to alternative routes. So if I have this first route and it comes as down, we delete it. All right? And then what we'll do is we'll add another interface. We'll use another fallback one. Okay. So regional internet access. So let's say I have multiple egress points and I want to route all traffic through centralized firewalls, right? As indicated here. Because sometimes, especially if in a banking situation, we're not going to want those branches any direct access to the internet. But also not globally in a single point. I don't want all internet traffic routing through one firewall here, and then that guy we lose this firewall, and then they lose all their internet access. Because a lot of these organizations are actually doing quite a bit of their work in the cloud as well. So, for example, let's say all branches in the United States use an internet exit, but European branches use a European internet exit, right? I don't want to route the European users through a US internet point. That's horrible. Yeah, that would be bad. So several options are available to achieve this, but they're all based on advertising a default route into the regional branches. You can advertise this route as shown previously or by a firewall. Within a region, you can have a redundant set of internet access points. Load sharing is also possible. Regional internet access allows for maximum flexibility when you're designing internet access. And in summary, you can provide internet access with or without network address translation in a set of central sites, or in a set of regional sites, or for each branch office. You can use those existing firewalls for NAT and for providing default routing. You can control that selection of various internet access points flexibly through routing policies. And that concludes the section on network address translation. It also concludes the section on policies. Remember, policies are going to define fine-grained traffic control and a vast number of features in an SD-WAN. We can enable flexible choices of topology, traffic engineering, and service insertion. We also support traffic-based traffic engineering, policing and shaping, automatic application-aware routing, quality of service, and adding stateful or stateless firewalls. We also select the best path based on path quality using a set of metrics. And you can configure direct access locally, per region, or globally with network address translation or with flexible routing. Thank you for watching, and that concludes the section on policies. Stay tuned for more SD-WAN content.